delta epsilon s in one earthquake, as the strain builds up, and if strain exceeds the strength of the material there, eventually you have failure, big earthquake. And at that point, some strain is released. And this change, delta epsilon s, is another important quantity. So to the first order, we can really look at this problem using only these two parameters, epsilon dot and delta epsilon s. Well, then the first question is, how big is strain rate is? And of course, strain rate varies tremendously from place to place. But for large events, magnitude 8 or larger, major plate boundaries are involved. And at major plate boundaries, strain rate is relatively uniform. For example, in case of Japan subduction zone here, for some time by now, lots of GPS measurements have been made. So we know how much strain is accumulating per year. So if you look at this vector from here to here, over a distance of 250 kilometers or so, the change in the vector is approximately 5 centimeters per year. So the rate, if you take the division, is 2 times 10 to the minus 7 every year. And this number is really key in seismology of this kind. 2 times 10 to the minus 7 strain every year. So over here, it's strained at this rate. And eventually, once every 100 or 1,000 years, this strain reaches the delta E epsilon s so that a large earthquake can happen. So this is a convergent plate boundary. And more or less the same rate applies to strike slip boundary, like Sandler's fault. And in case in the intraplate zone, within the plate, Taiwan has everything, but inland earthquakes are sort of within this portion. In that case, strain rate is much, much smaller, and order of magnitude is smaller, so like 2 times 10 to the minus 8. Well, how about then the other parameter, delta epsilon dot? How much change in strain happens during an earthquake? And actually, this dates back to 1927. Professor Tsubo wrote a very nice paper in 1930s by looking at these geodetic measurements, excuse me. And if you see these vector diagrams these days, you can immediately say, wow, this is GPS data. It's not. Of course, in 1927, there was no such thing. So this was done by triangulation and also some leveling for the vertical. So it was an enormous amount of work those days. But anyhow, they could determine the change in the position, horizontal position of the benchmarks over here and over here. And there is some difference. It's a bit asymmetry, but this asymmetry could be due to where the reference point was chosen. So let's ignore that kind of detail. So this vector here is about 2 meters or so from one side to the other. And this change happens over a distance of 20 kilometers or so. This is a spatial scale. So over 20 kilometers, the change in the displacement is about 2 meters. That means the strain change is the ratio of these two. That is about 1 times 10 to the minus 4 here. And also, this number is not quite universal. For subduction zone events, this can be smaller, 1 times 10 to the minus 5 sometimes. And in some exceptional cases, this can be larger than this one. So this will give you just one kind of range, one representative value, and there is a range. So if you look at that range, it looks something like this one. Plate boundaries, major plate boundaries, E dot is about 2 times 10 to the minus 7. And the plate interior, as you go inside, it can be smaller by an order of magnitude. So it's 2 times 10 to the minus 8. And change in earthquake, the example I showed you was 1 times 10 to the minus 4. However, it ranges from 2 times 10 to the minus 5 to 2 times 10 to the minus 4, depending upon the type of earthquake you are looking at. So there is a very large range. So that's the reason why the style of seismicities and style of earthquakes can be very different from place to place. If in one place, if everything is happening more or less uniformly in time, then you can compute repeat time tau, which is the ratio of these two parameters. And if you divide this one by this one, you get about 100 to 1,000 years for major plate boundary. And this number sort of agrees with our more or less common sense. In Japan, magnitude 8 type earthquakes can happen more like 100 to 200 years apart. In Chile or Alaska, it can be much, much bigger. And repeat time can be 1,000 years or so. And this was San Andreas, more like 300 years or something. So this number, very rough number, obtained by the ratio of these two key parameters, is more or less consistent what we think we know. And the plate interior is more difficult because strain rate is very small. And of course, delta E epsilons may be different from one earthquake to another. So we can only get a very approximate number. But nevertheless, you can easily tell that this can be much, much larger, like 1,000 to 10,000 years or so. So in a way, this is a physical process we are looking at. And we are looking at relatively infrequent events. That's a difficulty in seismology. We understand overall physics of the process, but the process is relatively small over a long time. However, an earthquake happens abruptly in a very short time. So we have long-term process and short-term process happening at the same time. That's the unique character of the science. Okay. Let's look at the geological long-term process. What I showed you are essentially based upon geodetic and seismological studies for the last 100 years or so. And the question is whether is this stationary in time? Can we see this evidence on long-term geological processes? And of course, I'm not a geologist, and I don't have much expertise in understanding the process. However, this one is my favorite slide. And a friend of mine, Dr. George Pravka, actually loaned me this slide. This is my favorite. This is just amazing thing. Now, this is Middleton Island, Alaska, and it's taken from there. And this shows sequences of marine terraces. One here, the lower level, and 2, 3, 4, 5, 6. At least you can see 6 terraces. And the step here, the lower one is only 3.5 meters, but over here you can see much bigger one, up to 9 meters. It varies, not quite uniform. And these have been dated with various methods. And the interval between these terrace formations from 500 to 1,350 years. So again, it's not quite uniform. It varies. Some cases, interval is shorter. Sometimes it's longer. So this, but however, this is pretty spectacular that we have a geological record of this type of repeating processes, long-term strain rate, interrupted by sudden change in strain, which is an earthquake. So this is my favorite. And this is the interpretation by Pravka and his colleagues. Horizontal axis is the age, and 0 is present. All right? And this one is, what did I do? This one is average terrace height from 0, 10, 20, 30, 50. So there are stepwise changes, and 1, 2, 3, 4, 5, 6. So overall, this is a long-term strain rate. However, it's not completely uniform or continuous. You do have discrete processes producing an earthquake. Well, whether you think this is regular or not, it depends upon your judgment. Long term, this is very regular. However, if you look at very carefully, of course, it's not completely uniform. It varies from 3.5 to 9 meters, and the interval varies from 500 to 1,350. So in terms of our real life, this is very irregular because the repeat time is 500 and 1,350 makes a big difference. But as a geological or physical processes, in a way, this is surprisingly regular. The nature our nature works in a rather regular fashion. Strain accumulates very continuously, uniformly, but this failure happens once every 500 to 1350. So the process I described in the beginning, on the basis of the data we have for the last 100 years, has been continuing for a long time, and it will continue in the future too. Okay, so if we put it in this diagram, it's a very simple process. Strain increases as a function of time, E dot, and if this reaches strength, there is a strain drop here, which corresponds to an earthquake, and so on. If everything is regular, we have regular process, and it's very easy to make a forecast, and this is called deterministic behavior. And as I have shown, in nature, it's not completely regular. There is some undeterministic or non-deterministic element here, but if the process is close to deterministic, this may be fairly regular, and you can make reasonably reliable, accurate forecast regarding seismicity for the next 100, 200 years. And there is that element in nature. It's not completely random. Okay. Well, so if some region, like Chile or Alaska or even Japan, if the system is dictated by deterministic process, or if deterministic element dominates, some forecasts are possible, as you can see. And how do we make forecasts? Of course, we have to measure strain build-up, delta E, with GPS these days in area over S, over what area strain is accumulating. And we can do this very well these days. In Taiwan, Japan, California, every place, we have a reasonably good idea regarding where strain is building up. The second is if delta E is comparable, becomes comparable to the estimated seismic strain change delta epsilon S, of course, it's going to break sometime. So we can make some forecast of an earthquake with some magnitude, which depends upon not only delta ES, but also the size of the area. If the strain accumulation is localized, it's not going to be a very large event. But if strain accumulation extends over a large area, you are going to have a large earthquake. So if deterministic process dictates, we can make some forecast. And of course, in a way, this is may look obvious. However, it wasn't that obvious 100 years ago, or even 50 years ago. And also, we didn't have measurements. The geodetic measurement was extremely difficult. And there was no way to know what the plate motion is. So only recently, this whole process can be now understood fairly quantitatively. So even if there is fluctuation, this deterministic forecast is very important if we want to understand earthquake process in a fairly solid physical framework. And that's a big progress in this science. Well, one really good example is the 2010 Maui, Chile earthquake, magnitude 8.8. And this paper by Reg and others, 2009, is really a very impressive paper. And this particular location is very special. This is South American coast. This is 1960 Chilean earthquake. So 1960 earthquake is the biggest earthquake for the last 100 years or so. And then to the north of it, this section, 1835, there was a big earthquake, magnitude 8.5 or so. And this one became very famous because Charles Darwin happened to be near Concepcion in this area. And he basically felt it, he documented it. So it's very well known, even if it was in 1935. And since that time, there hasn't been really major earthquake on this plate boundary. This 1939 is a different kind of event I will discuss later. So in a way, this portion, for more than 100 years, nothing happened. And thanks to GPS, they started GPS measurements in 1990s and found strain is accumulating more or less corresponding to the plate rate. So they can make some forecast in the way I described in the previous slide. So this Charles Darwin gap, 1835, they found the strain is accumulating. And if you express it in terms of slip deficit, there must be 12-meter slip deficit over this blue zone here near Concepcion and also near Santiago over here. So now we know the total strain. You can make some estimate of the total strain rate, even if the GPS measurement was limited only for 10 years or so. However, if you say since 1835, the same process has continued, you can extrapolate it. And you know the area, so you have delta ES and area over here. You can come up with magnitude. And the magnitude they came up with 8 and 8.5. And biggest uncertainty is, as I have shown in the Middleton Island, exactly when the next earthquake is going to happen is somewhat uncertain. We can say within 100 years, but that's a bit too vague. So the reason why this paper is more credible is they have a statement that if the event is to occur soon after this paper was written, then this would correspond to magnitude 8 to 8.5 earthquake. So this is a very reasonable physical statement because they have measurements over some area, and they make this assumption if the event is to happen soon, then it has to be this magnitude. And then surprisingly enough, the paper was written in 2009, and then 2010, magnitude 8.8 earthquake happened in this red zone, more or less. So this is exactly where the slip was predicted. So I think by any standard, well, some people still may say, well, this is just by coincidence, maybe. However, by any reasonable common sense, I would say this is a good forecast on the basis of physical measurements, on the basis of physical theory, and everything. So I think this is a very important paper in this kind of science. Then similar forecasts were made for Costa Rica. This is Costa Rica. And then they have been doing GPS. There are also papers, Prodi, Inuma, Nora Buena, and others. And lots of papers written. And they all made a very similar forecast, so very credible. And in 2012, in this case, they made forecasts on the basis of their measurements that the MW 7.8 earthquake is going to happen in the area where strain accumulation is highest here. And indeed, in the same year, 7.6 earthquake occurred right here. So again, by standard common sense, this is a very good forecast. It's a very difficult thing. We are dealing with natural process, which is controlled by many other factors, but still on the basis of physics. And both data and theory, they made a forecast. In this case, that happened. So I think the science is working, but there's another aspect of science. That's a problem. Well, we encounter difficulty when interaction between segments differs from sequence to sequence, as I will explain to you what this means. Well, earthquake process is very complex. It's not one just boundary where strain is being accumulated. There are lots of patches, and strain accumulation is different from one patch to another. That's the cause of difficulty. Well, this became very apparent very quickly after this event. In 2014, in March 2014, some small events started happening. Small in this case, almost 7 here in South America. Oh, I'm sorry again. Near Peru, over here, near Chile, I'm sorry, Chile-Peru border here. And this area actually had been looked at by seismologists for a long time because in 1868, there was 8.5 to 8.8 earthquake over here, over a very large area. And then 9 years later, 1877, there was another one over here. And then nothing happened since that time, well, except over here. So this particular, the southern segment, has been watched as what we call seismic gap, because more than 100 years ago, something happened, and since then, nothing happened. And then more recent GPS measurements indicate strain is accumulating. So in a way, people knew that something was going to happen. So if they wrote a paper like RUEG, they would have said, if the strain accumulates over this entire area, over here, they would have said magnitude 8.7 to 8.9 earthquake would happen. Although no one really wrote the paper, however, everyone had that in mind. So when this small earthquake started happening in March 2014, actually I was on the way from Taiwan to the US and stopped in Japan, they were discussing that. So we were aware that something was happening. So the simplest way is to make forecasts because we knew this, but no one said that. And then what happened here was in May, there was magnitude 8.1 earthquake. Ikiki, I keep making a mistake, over here, right here, only this limited portion. So in this case, the gap was much bigger, but the actual event was much smaller within the gap. So what happened is we drew this ellipse here, but this core elliptic region is not uniform. It's actually, it consists of small patches. And in this particular case, only these 1 or 2 patches fail, but there are other patches which didn't fail. So obviously, this result indicates that there is very high seismic risk over here and over here, because strain must have accumulated over here, and we know the strain has accumulated, but nothing has happened. So this is the difficulty. We can make some forecasts, but it can't be very precise, not only time, but also the location and size. So this is because there is some non-deterministic nature in the process, in addition to deterministic nature in the process. Well, even more spectacular case, the 2015 Nepal earthquake. And of course, this Himalayan front seismic belt here has been watched by many people, particularly Bilan and others, Bollinger and others. They have been studying this area very extensively. And there are places where major earthquake happened in history. In particular, this one, 1505, there was a large event here. And then nothing happened since 1505, so more than 500 years has elapsed. So if you make it likelihood over this section, 8.6 earthquake would be most likely to happen here. So if you look at this entire zone, in a way, it wouldn't be surprising to have big earthquake. Any point along this boundary, any place is capable of generating large earthquake, and nothing has happened, and the strain has been accumulating. Then this 2015 Nepal earthquake happened where? It happened over here, which is the least likely place by common sense, because over here there was 1833 and 1934 event very close to it. So this is the least likely in a way to have a large event, but it did happen. So again, this indicates that the plate boundary is not really quite uniform. There are lots of patches, some large, some small, and sometimes only small patches fail, producing magnitude 7.9 earthquake, like Nepal earthquake. But sometimes some of the bigger patch might fail, producing big one. But then that might trigger adjacent patches to grow even bigger earthquake, like 1505. And this is inevitable because the process, not only process, but the structure we are dealing with are not uniform. There are lots of small patches, and interaction between those patches produce this non-deterministic behavior of the process. In a way, this has been well known in physics, and even since the time of Poincaré, well, 17-something. So intuitively, this is obvious. We have lots of patches in a large system, and if they interact, behavior is somewhat unpredictable. It depends upon interaction between different patches. Very often, we compare this to traffic accident in the big freeway. There are lots of cars, and of course, some accident will happen. However, whether this will become a big accident or not depends upon how far the effect will propagate. If the driver behind the accident site is careless, he will hit rear end, and then effect will propagate. So that kind of process is not completely predictable. It's a physical process, but it's difficult to predict. So because there is that element in the earthquake process, for that reason, forecast becomes very uncertain. Well, this is the kind of thing we have to live with. We can't get rid of it. Okay. Well, so triggering of multiple asperities, this is another problem. This was somewhat unexpected. The one I mentioned, this triggering, we have one event, and that might trigger another one, and so on. So in that case, you might think the overall size may be the sum of each event. That's a common sense, right? However, history tells us that that may not be the case. If you have three patches, and if they break together, it produces an event bigger than the sum of three patches. And that was based upon a very qualitative study for the 1906 Colombian earthquake. We noticed this with very poor, low-quality data, so conclusion could have been wrong. In 1906, this is offshore Colombia, South America. In 1906, large earthquake happened over this segment, over nearly 600 kilometers, and that produced magnitude 8.8 earthquake. And the same segment broke in three events, 1940 to 1958, 1979, small patches. And if you sum up the seismic moment for three events, it's only 20% of the seismic moment of 1906. So this is a rather peculiar situation. We have three patches, and if they break simultaneously, you'd expect event 3 times bigger than each one of them, but it's much bigger, 5 times bigger than that. Well, at that time, we thought, well, this is what happened. But in modern terms, this behavior is often called conditional stability. Well, that's can be some ambiguous term. But in between, it looks like it's slipping all the time. However, when a brittle event happened, then that same segment can also behave like a brittle material. And this became very apparent during the 2011 Tohoku earthquake. Now, this is a very nice paper written by Loveless and me. But this one is written after the 2011. But their data show, even before that, if we could interpret their data beforehand, we could have interpreted this way. This is actually very interesting. The C, which is called the coupling constant, this means the fraction of the slip that is seismic. So when it says 0.3, only 30% of the plate motion slips seismically, and 70% will be creep. And in Tohoku, it so happened that over here, pretty much low, 0.3 over here. So over this segment, this portion slips more or less aseismically, and only this portion is coupled strongly, and you can expect 7.8 or so. So in a way, this was a picture we had. Since this is a creeping, maybe we don't expect really big earthquake. However, what happened is when this failed, it triggered slip in the area surrounding it, and it grew much bigger event. So this is most like this Colombian kind of situation. It's not a uniformly coupled zone. The coupling happened at discrete size, and the surrounding area, normally it's slipping, creeping to some extent. But when brittle failure happens in one asperity, it triggers slip in the surrounding area, which is normally slips, creep. So this adds another complication, because we can't really judge from the size big the earthquake is going to be. Sometimes it involves much bigger seismic slip. Well, so this kind of variability remains, and I don't think we can really get rid of it. We have to live with it. So the point is, on the basis of modern measurements and modern theory, we can make reasonably good forecasts. But uncertainty exists, and as a result of this uncertainty, variability remains. So we have to live with it. We can't make very deterministic prediction. We can make some forecasts. We always have to allow for large uncertainty, and that uncertainty must be communicated to the public properly. Okay, so what is the cause of variability? Go back. It's a non-deterministic process, like triggering, that sort of thing. So non-deterministic behavior is caused by interaction of many elements, like slip patches or asperities in a large system. And this is really the element of some chaotic system. In many cases, it's deterministic. To some extent, everything must be controlled by physics. So to some extent, everything is deterministic. If you know the structure, if you know the physics, you should be able to predict. However, in the real world, we cannot measure everything. So there are some parameters which you cannot determine. So as a whole, overall behavior becomes non-deterministic. And that's the cause of non-deterministic behavior. So that behavior comes from complexity in plate boundary structure. And this complexity in plate boundary structure can be inferred from a seismicity. Or these days, we can use seismic slip inversion to determine how complex the plate boundary is. Before slip inversion became possible, we inferred it from seismicity. How did we do that? Of course, we could determine the detailed slip inversion as we can do these days. We have to look at seismicity in the past. And this is a seismicity map of the world. And these dark zones mean the slip zone for a great earthquake, like Chilean earthquake 1960, 1964 Alaskan earthquake, and some small events in Japanese earthquake and so on. So interpretation was, well, for some reason, along this subduction zone, patches are relatively small. But in Alaska, as we have seen the Middleton Island, patch is very large, over 500 to 1,000 kilometers. And in case of Chile, as we have seen in 1960, this extends over 1,000 kilometers. So this size is very different from place to place. So if the size distribution is different, the way they interact can be different. So that means behavior or the style of seismicity can be different from place to place. And to make it in a sort of sketch, the cartoon-like picture, we have this. Well, this is the figure Thorn Lay and I wrote many years ago. Well, in some places, like Alaska and Chile, it's fairly uniformly coupled, not completely uniform, perhaps. So this thing tends to behave always as a unit. So the behavior is more deterministic. However, in some subduction zones, like Solomon Island or Aleutian Island, it gets smaller like this one. And normally this area, slip is quick, and the brittle failure happens here, or strain accumulation is mainly here. And sometimes in this case, you have unpredictable behavior. Normally, these will go by itself, so repeating magnitude 8 type earthquake, but once in a while, they happen together, producing much bigger event. 2004 Sumatran earthquake is one of them, I think. Sumatran subduction zone is not uniform. Going from Sumatra to Andaman Island and Nicobar Island, there are different sort of patches, but in 2004, the failure of large patch offshore Sumatra seems to have triggered events to the north, so that the event became very large. In Japan, it gets more messy. Small ones, large ones, and we thought, well, at least someone thought, because Japan would never have bigger that's a kind of rather superficial view. If you know this one, if something happens here, it may trigger this whole thing to become a big earthquake. But in that sense, the big earthquake that happened here, like Chile, or big earthquake that happened in Japan, may be different in nature because the structure that produces the events is different. And this is a very interesting research subject, and we don't quite understand yet. So, in a way, this is a working hypothesis. We can never determine this. We cannot go to great boundary to map this one. So this is a working hypothesis, and we have to go ahead with this one to see whether what happens in the future would be consistent with that. But so far, I think this general behavior is still valid, I think. And as you go to Marianas, for example, there is nothing, so you don't have a big earthquake. Well, there is some difference in opinion. Some people think Mariana and Chile are the same. There is no reason to believe that Mariana is not going to have big earthquake. If you wait 100,000, 10,000 years, eventually even this place may produce this one. So we can test in the next 1,000 years or 10,000 years. But for the time being, personally, I'm still going with this particular hypothesis. But you can challenge it because we don't have really direct data. But at least we found this very useful idea. But to really understand the behavior of this system, we need to at least understand two things. We need to understand this difference, how different it is from one place to another by using seismic imaging, for example. And secondly, what is the real physics of the behavior in this zone? I said the conditional stability. That means normally it's creeping. But if it's triggered by adjacent asperity, it can slip as a seismic event. Some people think they understand it, but I don't understand it. So it will be very important to really understand this whole physical process so that we can make much better understanding of seismicity. Well, with this non-deterministic element, we do have irregularity. This is the deterministic thing, and everything goes sort of like simple dictation. And as we have seen in the Middleton Island terraces and others. However, this is what we see in some parts of Japan. It's very complex, and it's very difficult to make useful forecast. Okay. Let's see. How does it go? So what, 90 minutes today, right? Right. Okay. So basically, this is the way we really understand, and it's a hypothesis. You can't really determine everything completely. So this is a very unique feature in earth science because we can't experiment and we can't go there to really determine it, to verify it. So in a way, some people think it's unfortunate that this science is not verifiable. Well, but in other sense, that's an interesting aspect of the science. We can always think about it, and we can come up with a hypothesis and then try to interpret what's going to happen. And so it's a matter of your choice. If you don't like that, maybe you should do something else. Okay, so this is a summary of this process. Deterministic part. There are two length scales in physics. One is spatial length scale. It's a fourth dimension, or the width of the coupled zone in subduction zone. And time scale is dictated by plate motion. So we have two distinct scales, one in space, one in time. So in terms of physics, you can produce fairly deterministic forecast, regularity, predictable, but still uncertainties are hard to quantify because there are elements which you cannot determine. And the behavior would be, I make a mistake. It's something like this one, all right? And the non-deterministic part, we do have this element, but in addition to that, the fault interaction becomes very important because there are lots of patches in a very large system. Non-linearity of rock, this conditional stability type argument, the same material sometimes creeps, but sometimes fails simply to failure. And this is a non-linear behavior. We don't know completely. system, so it's very difficult to predict deterministically. However, some behavior is predictable to some extent. That's magnitude-frequency relationship, as I will show you next. If we have lots of elements in a big system, and you allow interaction between different elements, you tend to have magnitude-frequency relationship that is dictated by power law. Power law means energy, the number of events with certain energy is proportional to the energy to the power of some constant. I will show you. So that in seismology is called Gutenberg-Richter relation. Large earthquakes happen less frequently than small earthquakes. So in this case, we can predict only in a statistical sense. We cannot predict each event individually, but we can predict overall behavior of seismicity, for example, in terms of magnitude-frequency relationship or Gutenberg-Richter relationship. So this is essentially what the earthquake process is. And in a way, many people think we have known this for years, maybe. But now, we now have much better physical concept and much better data and much better theory, so that at least we can understand these quantitatively, so that we can make much broader application. I just want to explain to you why we can have magnitude-frequency relationship. And this is a kind of subject with much bigger context. And the physics people who are interested in chaotic system, they say chaos or chaos. That's a deterministic chaos. Everything is deterministic, but the system is nonlinear. So that if you change the initial condition by small amount, the final result can be very different. So this is a very nice discipline. However, in case of seismology, I think this is used only to produce magnitude-frequency relationship. And the magnitude-frequency relationship we see in seismology is a result of non-deterministic behavior. And so interaction of many elements in a large system is important. And what is interaction? Interaction can be in many different ways. In the simple slider block system like this one, we have a slider block here sliding on this plate. And the slider block is driven by upper plate like this one. And if you move it, eventually one slider block will slip. And this is one earthquake, but sometimes this one slip can trigger a slip of adjacent slider blocks, so that as a whole you have a bigger event. It's easy. But in this case, interaction is given by differential equation. You can set up differential equation for each discrete system. You couple it by spring. So everything is deterministic in a way. You can set up a system of differential equations, and the interaction is given by differential equation. This is a slider block system with many elements in a large system. Or sometimes you say only probability. You can give probability of this one to trigger the adjacent one. In power correlation theory, they do that. If one element moves, that effect can be transferred to the adjacent part by given probability. In this case, you don't solve a differential equation. Or in cellular automata kind of argument, you set up a rule and then go ahead. So, of course, the consequences are different between those three. However, as far as magnitude-frequency relationship is concerned, it's basically, this will lead to power law. In power law, as I wrote here, the number of events is proportional to energy to the power of some constant. In case of earthquake, the constant is -5/3. And if you take the log scale and you introduce magnitude, you have magnitude number relationship. Log n is equal to a minus bm. This has been known for nearly 100 years. Okay, so how well this thing works? But, yeah.
But the number of events, the energy is total energy of those number of events?
Yes.
Or? Okay.
So usually in seismology, However, the original power law is given in terms of energy and number.
The total energy of the total
Yes,
event.
energy of the system. Well, maybe I can explain this better. I don't know. So, for example, if we have only one element, it's a characteristic. Nothing else happens. So, in terms of magnitude, every earthquake has the same magnitude, nothing else, because you have only one patch completely isolated from the rest of the world. So, we have only one point here in the red. It's a discrete. If you take cumulative statistics, it will be like this one. This one is events with magnitude n or larger. So if you take log of number here and magnitude, it will be flat if you have cumulative, but if you have discrete, you have 1 point. Let's just look at only discrete, it's easier to understand. However, it's non-characteristic, it's completely non-characteristic. Usually, that type of modeling can produce magnitude frequency relationship. Log n is given by A minus Bn. B happen to be close to 1 in many cases. But it depends upon how you define magnitude. So you have to be very careful about that. However, these are the two end members. This is the characteristic. Like if we say Chile or Alaska, but the whole big patch fails regularly. Middleton Island case could be closer to this one. There is some fluctuation, only one magnitude. However, in case of Japan, it's more like this because we have small one, large one, everything. However, in the real world, it's a mixture of this one. So if you combine these two, we have this and something funny here. It's a characteristic portion. At large magnitude end, it doesn't follow this trend. And do we have this example in the real world? And a very good example is from the Japanese Kanaishi repeating sequence. This is a very exciting thing. This is the northern part of Japan, Kanaishi, and almost on the coast, just slightly offshore, I think. The city of Kanaishi around here, and the group at Tohoku University, Matsudawa, Uchida, and a lot of people discovered that in this particular area, magnitude about magnitude 5 earthquakes repeated with very regular interval of 6 to 7 years for nearly 60 years from 1950s. Well, it's really quite impressive thing. This one, almost the same magnitude and almost the same interval. If you look at seismicity, you can tell this repeater happened here, and nothing happens surrounding it, right? All other events are at some distance away. So in a way, you can consider this as a closed system, isolated system, without any interaction with other parts of the world. Well, sometimes some scientists are like that. He's working in complete isolation without any interaction with the rest of the world. Well, so he can publish paper intermittently, the same paper over and over again. But you begin to interact with lots of people, you introduce lots of information, and you have magnitude frequency relationship. Some paper is important, some papers are not important, but lots of papers. So it's the same thing. This basic physical principle applies to any system. The question is which side you are. And in case of seismicity, in some parts of the world, its situation is more deterministic. But in other parts of the world, it's less deterministic. So you have to take into consideration that the variation and diversity in any hazard mitigation practice. Well, if in this case, if you look at more detail, not only these repeating events, there are lots of small events. And these are caused by more or less non-deterministic factor once you go to a smaller one. And Dr. Uchida produced this figure for me. So if you take the whole thing and makes magnitude frequency relationship, it goes very nicely, the power law, up to magnitude 3.8 or so, but the large events are different. Because this is controlled by this repeating sequence. But this one is controlled by small events. And this sequence was completely destroyed by the Tohoku earthquake 2011. This lower diagram is a blow-up of this portion. Tohoku earthquake happened here. And when it happened, there are a lot of magnitude 5 to even 6 in a short time. So this regularity was destroyed completely. And if you blow up, it looks like this one. It's much, much shorter interval. This is 1 year here. So within a year, there are 6 or so events about magnitude 5 to 6. So even magnitude is now more variable from 5 to 6. Before that, it's all 5. And this interval was, of course, very. So this is a very nice example of a physical system that is governed by this kind of process. If it's completely isolated from other parts, it produces regular sequence. But when Tohoku earthquake happened, the creep tends to into this creeping strip tends to go into this area, then this regularity is destroyed because it's not an isolated system anymore. So this is really exactly what's happening in the real world. Well, other parts like Nankai Trough, where Japanese government is expecting another big magnitude 9 earthquake. It's near Osaka here. If this is from Professor Ando here, the magnitude frequency ratio goes like this one, and then there is some characteristic thing. That is, this plate boundary has very distinct sort of patches. One is Nankai to Nankai here, the other one is Nankaido. They tend to happen more or less regularly. But in addition to that, there are some small events over here. So as a whole, if you take magnitude frequency relationship, it's a mixed pattern. So this is probably the real world, but we have to be aware of this one. Okay, now let's go to next domain, domain A earthquake. As I said, domain A is here, near the trench. So most ordinary megathrust earthquake happens only here. However, the real big one, like Tohoku earthquake, actually slip here was relatively small, almost nothing to the first order. Main slip happened here. Well, there was some slip here. And the Chile or Alaska earthquake, 1960 Chilean earthquake or 1964 Alaskan earthquake, 2 biggest earthquakes in the last 100 years, probably slipped both over here and over here. Although sometimes it's hard to distinguish. And Sumatra earthquake, the same thing. Probably both domain A and domain B are involved together. So they look really great earthquake. However, sometimes nothing happens in B. Only this portion breaks. And that produces a very unusual earthquake. So this domain A earthquake, we call it tsunami earthquake because it produces a big tsunami because deformation is close to the trench, close to the water. So if we have a slip here, it produces a big tsunami. But not only that, over here, the slip is pretty much aseismic or slow. So the ground motion comes from this event is relatively weak. So people don't realize it as an earthquake. And then big tsunami came to the coast, killing more than 20,000 people in case of 1896 event. And this one is pretty much non-deterministic because strain accumulation is very different from here. Strain accumulation here is pretty much, it's locked. So if you know the plate rate, you can more or less predict what the strain accumulation is. But over here, a large portion of that is aseismic. So strain won't accumulate due to plate motion. And exactly how it's partitioned, creep and slip, is not known. And we don't know yet. So for that reason, there is a tremendously large non-deterministic element here. You can't make prediction regarding what the average repeat time is. So again, we have to live with this one. This always came as a surprise. And of course, it was surprising back in 1896 when Sanriku earthquake happened. The best example is this. Unfortunately, this is just before instrumental seismology. There were some seismograms that quantitated very difficult to understand. However, the reports are very clear that this has a very strange behavior. Well, run-up was very high, up to 30 meter over 200-kilometer section along Tohoku coast here. This is very similar to 2011 actually. And there were people, what happened towards evening, so there were lots of people on the beach, and they did feel it, very slow ground motion. But since it was so weak, they didn't pay much attention to it, and 30 minutes later, big tsunami rushed to the coast, and more than 20,000 people died. So this is a very typical behavior of what we call tsunami earthquake. So seismic magnitude is only 7.2 because ground shaking was very low. However, tsunami was one of the largest. It's almost comparable to 2011. 2011 Japanese Tohoku earthquake was bigger, but not much. So this is a very difficult event to deal with in terms of tsunami because you don't feel seismic wave. So seismic magnitude is small, you don't give warning, then big tsunami happen. But also, this is pretty much non-deterministic because we don't know exactly how strain is accumulating. Most of the strain is released in creep. All right, and this is another one. Okay, I forgot to mention this one. Now, this is a domain A earthquake, which I will discuss in more detail later. And also, there are two locations where we have intraplate event, 1 and 2. And these events are also very special in the other way. They produce very strong shaking. So even if magnitude is not very large, ground motion is much, much bigger than you'd expect for the magnitude. And a good example of that happened during the aftershock sequence of Tohoku event. This shows the contrast between domain B, the regular megathrust earthquake, and intraplate earthquake, where in this case domain B is actually Tohoku earthquake. So this is the main shock, 9.0, which happened somewhere around here, and produced this PGA here. And PGA is very large over large area, like some places it's more than G, but over here very large. And this is one of the aftershocks that happened on April 7th. Main shock was March 11th, so about a month later. And that happened in the intraplate region. And this produced very strong shaking. In Sendai around here, actually PGA is bigger for this event than this. And the magnitude is only 7.1. So this is a characteristic of intraslab event. And we have experienced over and over again. So understanding this kind of diversity with a variation of a source spectrum is very important because the diversity is whether event is in domain A or domain B or intraslab. And in terms of shaking, you need to understand the source spectrum. Of course, in those old days, 1896, or even just 50 years ago, even 30 years ago, we didn't quite know what the source spectrum was because we didn't have broadband instrumentation. We determined the size of an earthquake only by using magnitude, only one spectral point, one frequency. But in order to really understand this diversity, it's essential to determine the source strength over the entire frequency band, and the source strength is essentially source spectrum. And this is the illustration. Okay, how do we determine kinematic source model? And this is very well established, well known, and many of you are, of course, experts on this one. Well, we have an earthquake like this one producing fault. It's a slip on the plane, mathematically. So like this, we have a fault plane, and there's a slip. This side moves to the right, this side moves to the left, the offset here. So if you observe this motion in near field, point A, obviously you'd observe displacement like this one. This is the time of the earthquake. It moves to to this value, half d. D is a total offset, because one side moves this way, the other side moves this way. On one side, you get only half. If you happen to be point B, you have opposite one, minus half d. So this is the near field displacement, simplified A and B. But we seldom observe this one. At least some years ago, we didn't have many instruments. But these days, we do have instruments. However, most frequently, what we observe is this displacement at some distance away, far field, say over here, for example. In this case, we observe this one and this one simultaneously, but slightly infinitesimal time lag, because infinitesimally this side is closer to the station than this side. So just by adding these two, what's the minus sign, and dividing by infinitesimal time, dt, you have derivative of this one. So if you take derivative, you have this bell-shaped function. And this is what we call moment rate function. And this is what we call source spectrum. So source spectrum in standard seismology is defined by the motion at far field. But this is a time domain. If you take transform of this one, frequency transform, Fourier transform of this one, you have a spectrum. That spectrum is called source spectrum. So this slide indicates how moment rate function comes from this motion. And this area under this bell-shaped function is proportional to mu times d and s. D is the slip, s is the area, and this is called the seismic moment. So this area is proportional to the seismic moment, which is a parameter used to quantify earthquake at a very long period. Suppose if you have two patches like this one fading sequentially, the motion here would be stepwise like this one. You first have the step from one event, and then sometime later, you see the slip of second event. So if you take derivative at some far field, it will be two pulses. So if you see two pulses, it means the slippage was not uniform. And by doing that, you can determine how complex the fault plane is. In this case, you have two patches. You have this one. So in this case, it's more deterministic. In this case, if it's less deterministic, because sometimes only one patch may fail and producing small earthquake. So this is a slip inversion, and with the advent of slip inversion for the last 30 or so years, now we have much better understanding of the difference in plate boundary. Okay, to make it a bit more realistic, we have this. Well, the fault is actually finite. It's not just a very small patch. So if the fault is this size and the rupture starts from here and moves like this one. But still, the basic principle is the same thing. But each point, it slips like this one. So if you observe this at far field, instead of the simple bell-shaped function, you have some trapezoidal function like this one. And this total area is proportional to seismic moment. So this is what we call far field moment rate function. And sometimes this is called source spectrum. Okay? And very often in seismology, you take frequency transform of this one. And this is log of moment. And the horizontal axis is the frequency instead of time. And this is called moment rate function, moment rate spectrum. So this is actually the key parameter for understanding ground motion. What I want to emphasize here is in the past, when magnitude was determined at short period, in case of body wave, basically attempt, in a way, it is equivalent to trying to determine earthquake size by using over here at high frequency end, all right? You don't know anything about this one, only one frequency point. If you use 20 seconds, you determine here. And since 1960s, people started using seismic moment to quantify magnitude. Then it went extreme. Now they want to use a long period over here. So in the past, the size of earthquake is defined either course, engineers these days use much more sophisticated information than some years ago. But many years ago, most of the engineering practice was given by magnitude only. Magnitude is the only quantification parameter. And that was obviously very inappropriate because earthquakes have different spectrum. And if you use the strength of the event at one frequency band, you can't really understand the whole process. So with advent of broadband seismology, now we can determine this one completely. That made this whole science far more quantitative. And that's what we call diversity. Well, what will happen is this. By using this kind of very simple kinematic source, you can compute source spectrum for different magnitude. In this case, magnitude is defined by MW, which is the size of the event at a very long period. So MW doesn't tell you anything about high-frequency strength. It will give you the overall deformation only, static. All right? So that's a problem. You can't use that number to quantify strong motion. However, many earthquakes follow certain scaling relation, so that this is still useful. But anyhow, if you compute moment rate function, it varies something like this. Magnitude line, of course, long period size is very large, and it's flat over some frequency. This is 1,000 seconds, and begins to fall off. And at 1 second, it's very small. If you have magnitude 6.5, like a recent earthquake, it's flat up to maybe 20 seconds or something, and it begins to fall off. And at short period end, the difference is much smaller than long period end. So obviously, if you use only magnitude for strong motion study or hazard study, obviously there's a big problem, because in order to really understand the impact of an earthquake, you need to understand this entire spectrum instead of just one spectral amplitude at one frequency, like here or here. So that's a sort of progress in seismology for the last 20 or 30 years. Well, then we can have some important conclusion, because the tsunami, for example, is mainly controlled by long period, 100 seconds or longer. So this frequency band is very important for tsunami excitation. For nuclear power point, it's more like 1 to 10 hertz over this band. And for most houses, maybe somewhere around here, around the 1 hertz. And for tall building, from 10 second to 1 second range. So depending upon what you are looking at, your interest should be different. You have to look at the different part of the spectrum. But to be able to do that, you need to determine the source spectrum over the broad frequency band. And that became possible only for the last 20 or so years. And that's another progress in seismology. So before that, there was a big problem. Because of the insufficient data. Insufficient data means we had source spectrum only at one frequency, like magnitude, and the communication, insufficient communication between seismologists and engineers. We didn't communicate very well. Now, among seismologists, this kind of thing was obvious. But since seismologists gave only magnitude to engineers, well, these days, probably they give too much. But in the past, they gave only magnitude, and that's not enough. So for that reason, inaccurate messages were given to engineers. I'm not going to blame anyone. I mean, this is really our problem. We had poor communication. So because of that, even if each one of us has made progress, the joint effect wasn't that powerful. Well, what's a misunderstanding? I read a book written by famous Japanese engineer, Professor Osaki, who really spearheaded a high-rise building project in 1960s in Tokyo. Essentially, he pushed everything. The idea was the no earthquakes larger than magnitude 8.6 axis. I don't know why it happened, but seismologists must have told him. Because they used high-frequency magnitude, which saturates So no matter how large the event was, magnitude didn't grow. For example, Tohoku earthquake, everyone said it's magnitude 9.0. However, if you use the same old method to measure magnitude, Tohoku earthquake is only 8.1. All right, so this is completely correct. If you use old-fashioned way of determining magnitude, there was no earthquake bigger than 8.6. That was a big mistake or big miscommunication. And secondly, because of the very limited frequency band of instruments, long period ground motion was not measured, but through strong motion. So for that reason, it was believed that the ground motions do not have a strong long period component that would affect tall buildings. That means long period means longer than 3 seconds. Because there was no instrument. No way we could tell. But somehow that was put into wrong message that it doesn't exist. So it's really our fault. It's not someone's fault. And we need to have better communication regarding what we know and what we measure. And as a result, this is an amazing thing, actually. Professor Osaki's book has this spectrum. This is acceleration, spectral acceleration, or the biggest event one can think of in Tokyo. Believed to be the closing ground motion spectrum of a great earthquake in the 1960s. On the basis of these two premises, nothing bigger than 8.6. No ground motion longer than 3 seconds. So this spectrum has 0 amplitude at 5 seconds, but very strong amplitude. This number is incredibly large, 1800, all right, more than close to 2G. And however, at 5 seconds, 0. So this is a sort of in the back of mind of the people. So if you make building very tall, that should be okay because there is no ground motion which would affect tall building. However, for example, the recent Kathmandu record for Nepal earthquake, this is a record. And if you take acceleration spectrum, it has strong peak at 4.5 seconds. And this is really large, nearly 5 meters per second, half G, all right? So if you put that point here, over here, so this is really what happened in the real world. But back in 1960s, because seismologists didn't communicate well with engineers, it was believed that this could be the spectrum. And then high-rise building must have been safe because there was no motion. But that's really the history. And we should have really better communication to avoid this kind of problem. Of course, engineers are far clever than we think. So even if we gave them wrong information, they have good common sense. And that can't be real. So I'm sure in the design of real high-rise buildings, these things must have been considered to some extent. But still, this shouldn't happen. I mean, we are working in science, and we should give information, precise information. We should communicate in precise language so that we can avoid this kind of mistake. Okay. I don't want to say anything bad, but this is the history, and with the advent of modern seismology, we can now have much, much better knowledge about ground motion, and that should be communicated to engineers, and engineers can make good use of it, so it will be all safe. Well, how does it go? Maybe you have some question period, so maybe I can stop here and continue on tomorrow. Okay. So, well, I don't intend to blame anyone. I mean, this is what happened. And, but now we know what happened. We should fix it. Okay, any questions?
Thank you. Yeah, perfect. So very informative talk. So let's have a question and answer. And to make it more efficient, I would like to invite Professor Ma, maybe coordinate with me. Yeah, okay. With more communication. Okay, so we're open to the floor. Any questions?
If someone wants to speak Chinese, it's okay. I can translate.
Yeah, we do have engineers, so we have a very high
maybe I echo the first question. When we define...
Oh, I'm sorry. I can't hear anything these days. So you can speak.
Okay. Just about the patches.
Yes.
When you talk about these isolated patches, how do we can really define the patches in the seismicity behavior, earthquake behavior?
Well, the way it happened is, I don't know, people have different experience, but when we sort of noticed is when we are looking at doublet in Solomon Island, and as you know, many earthquakes in Solomon Island with magnitude of 7.5 to 8, they tend to happen in doublet. Within 1 hour or a few days, 2 events happen. And we thought there is sufficient interaction between patches, and each rupture zone is about 100 kilometers, and separation is 50 kilometers, and separation is about the same order. So that's how we sort of visualize the size of the patches and separation. But if they are close to each other, then they tend to happen simultaneously. So I think that's the first kind of hint we had from the doublet. And then in case of Tohoku, of course, if you remember, 1978, there was magnitude of 7.7 or 8, just very close to the coast. And that's a very well-defined patch. And before that, 1936 and 37, 2 events happened at almost same location. And then also 2005, there was another one there. So the idea is by determining, using slip distribution, slip inversion, you can determine the size. And they thought, well, this is a patch, and outside is creeping. And that was a picture before Tohoku. But what happened on 2011 March 11 was 7.2 earthquake happened over there. It's another sort of patch, but it triggered the slip across the trench. And that big patch near the trench, no one really knew, because presumably that was completely rocked for nearly 1,000 years, 700 to 1,000 years. But since it didn't produce any seismicity, no one would know, except GPS people were aware that there was some place in between trench and the coast. There was a large area where strain was accumulating. And they knew that. They did inversion, and there are more than 5 papers describing strain accumulation pattern. But since you don't have control in locating that from the land-based observation, the location was much, much closer to the coast rather than trench. So that's a limitation of the network. So to answer your question, I think it's basically modern days, it's based upon slip inversion.
I think we can make the patch map for Taiwan.
Yes. But Taiwan, probably there are small ones and large ones all over. But again, as I said, this is really working hypothesis, and we cannot really measure this directly. So that's the nature of our science. So there are 2 approaches. Our approach is to come up with some model, some hypothesis on the basis of limited data, and move ahead to see whether that will be consistent with the observations we will get. But the other approach, well, that's not good. Let's determine everything before we do anything. Well, there are people like that, and I respect that approach too, but it's not very interesting. So this is a standard process, and that is why we cannot make the deterministic forecast, because this interaction, part of interaction, this 7.2 and mentioned, and that interaction we cannot really predict strictly deterministic sense. Right? So if you look at the whole process after the fact, it looks like that 7.2 happened, that triggered, so you can call it a quotient. And there are many cases like that, but in terms of forecasting something, it becomes part of interaction, so you cannot use it to make forecasts. Yeah, to understand it as a forecast, you need to see the mention.
Just follow this question. That time we received some rate of change, for example,
Yes.
just before the last
Yes.
earthquake. But of course, you say that the current earthquake set time marker so that we try to see if there's something precursor prior to the last earthquake.
Again, the same thing. The precursor becomes the precursor if mention followed it. So if you really continue the same observation a long time, very often, presumably, this precursor thing happens from time to time, isn't it? Or
Can we get back to your slide? Show
which one?
And
Let's see. Okay, this one will work. Going back, you can tell me approximately where. Oh, yes. Okay.
where you plot the
Yeah, this is a very interesting observation.
Yeah, you know what I'm talking about. Yeah, can we check the back?
Do you use it?
I think that's Tohoku earthquake, right?
Yes, Tohoku earthquake happened right here, and this is a blow up here. It happened here.
Yep. And I think at this period, the experiment probability in detecting earthquake is quite confident. So we can say this phenomenon is real.
Okay, yes, that could be. Sure. Well, yes, that's what people call precursory seismicity. Yes. It is very possible that this is related to the mentioned failure, yes. So, but what I'm saying is it's very difficult to make deterministic forecasts on the basis of that alone. So this whole process probably indicates some preparatory process before big earthquake. But the behavior may be different from sequence to sequence. It doesn't happen all the time this way. And sometimes these things can happen, but nothing follows it. So for that reason, this, again, interaction, the way the things interact can be very unpredictable because there are so many elements. So that's why you cannot use that as a deterministic tool for a forecast. But it is certainly very important to understand the overall process for every sequence. So for scientific study, that's a very interesting and important observation. But to use this as a deterministic forecasting tool must be very difficult.
I see. But can I say, when you talk about the aspirity or the sleeping something, what you talk about today, is come from the long-term observation.
Mm-hmm.
Means so far maybe we cannot really check every temporal or spatial variation.
Sure. Well, yes. So temporal variation of not only seismicity but also all other geophysical processes would be extremely important for understanding how they lead to failure. But the way it works is really different You cannot have isolated system. If you have some precursory process and big earthquake process, in the same way for every sequence, for every earthquake, maybe you can use it as a deterministic forecasting tool. But the whole process is probably controlled by other things surrounding it. And that situation is different from place to place. So, but I agree. I mean, to really understand this kind of process is really very important. And unfortunately, sometimes some people who are against earthquake prediction tend to discourage that kind of study too. But that's bad. It's going too extreme. But what I must emphasize is there are so many factors involved. So the process is not unique. It varies from sequence to sequence.
Thank you.
Can I have another one? For the final slide, you have long period motion, and also mention that's important for engineer and seismology.
Just a second.
The last one,
Okay.
the Kathmandu,
Yes.
long period.
This one?
Is that, yeah, so
Or-
physically, this one, exactly. So physically, is it possible we can forecast the generation of the long period motion?
Well, in this case, if I'm wrong, maybe you can correct me. This is really most spectacular observation. And of course, I'm going to talk about tomorrow to some extent. This kind of thing was probably first observed in Mexico, 1985. There are two sites in Mexico City. One is very similar to this one. The period is 2 seconds, and the amplitude is comparable. And then close to it, there is another site where period is about 4.5 seconds, but amplitude is much lower, something like this one. But, and that's now to some extent interpreted as due to very shallow, extremely low velocity structure. Shear velocity is more like 30 meters per second. In this case, probably it's not that slow, maybe a few hundred meters per second, but it's thicker. But I don't think they really know now exactly what structure caused this one. So maybe, I think this is what I want to run. I just came here to run this kind of, what happened in Tainan, for example, could be certainly partly due to some site response, but also it depends upon what kind of wave came into that place due to source directivity and radiation pattern. So it's all integrated effect. But it so happened that all these factors work together to produce that 1 meter per second narrow pulse. So it is very important to understand the structure for better predictability of ground motion. However, that alone doesn't again tell you that this is going to happen next time, because the combination of this and source mechanism, geometry, and maybe 3D structure in between. So you need to understand everything. But that's what we are doing, and everyone is doing, right? Yes.
Okay, so any other questions? So,
My last question.
sure, please.
Sorry, just a very trivial question. Kanamori-san, how to enhance the communication between the seismologist and engineering? How do you think?
Well, I have my personal opinion, which may not work. Well, there are basically three ways. One is to have workshops and everything, inviting both seismologists and engineers. At least in principle, that should be a good way. However, it doesn't work very well. The second thing is to do it more informally, and that's what we emphasize at Caltech. Caltech is a small school, and we have seismology lab and engineering department. And so close to each other, we often see each other, and particularly in seismology course I taught, lots of engineer students came, and vice versa. So we train students so that they can be exposed to both seismology and engineering. And that's actually very important, because once you go into some particular profession, you tend to sort of defend your profession. However, if in the back of your mind, if you have training in seismology, for example, you understand what seismologists are telling you. So that interaction works much better. And that's a second way. And the third way is to have another sort of more formal workshop between engineers and seismologists. However, don't make any formal recommendation out of it. Just talk. Because if you want to make something formal, obviously, I mean, there are different interests in case of engineering. Engineers have to do something, right? Seismologists, they can talk anything. So the recommendation can be much more flexible. You can recommend something that cannot be done easily. But the engineers cannot take it. Of course, it's just impossible. So if you want to do formal way, usually nothing can be done. Nothing can be accomplished because the difference is so great. But if you do have more informal sort of workshop or something, without attempting to write any recommendation, anything, just to improve, promote our better understanding, mutual understanding, that was very effective. So my preference is to start training students in both fields, so that when they become professional engineers or seismologists, they do have knowledge from the other discipline. And that seems to be really the most important thing. And that can be done within one university, one area, yes. But I don't have really single better recommendation regarding that. Well, we are living in very different disciplines, so it's really inevitable, you know. And the engineers cannot change the opinion every day. Well, we built this building next day, but this is not safe, let's change it. But seismologists can change their opinion very easily. It's not a matter of irresponsibility. It's just we have to change our mind because we make mistakes all the time. But then we have to change it. But the engineers probably cannot do it because they have more solid responsibility to the society.
Yeah, I would like to add one alternative is that maybe we can work together for the same project, and that project should be solved, by our society. In that way, maybe it's a task, oriented, and maybe we can cooperate and to solve the problem. In this process, I think we can do better job. Yeah, yeah.
I think we begin the process a little bit. That's why we have the workshop here.
Okay, so I think about time, I would like to close the lecture today. So I would like to remind, tomorrow we have a lecture continue, the same place and at the same time. So let's give a big hand for Professor Kanamori. Wonderful. So thank you, Professor Ma. Do you want to say a few words?
So thank you for coming. And yes, tomorrow, the same time. And also, actually, Professor Kanamori will be in IES. Actually, the host is Professor Huang for 3 weeks in IES. So if any of you have questions or you want to have a further discussion, I think can be arranged. So just to mention that the possibility. Thank you. Okay.
不好意思，我们顺便广告一下我们这个研讨会。This conference will bring seismologists and engineering together, and to make some interaction. Yeah, it's in the coming August. 请大家如果有兴趣可以报名参加。我们那个哪里啊？Abstract 到3月15号，谢谢。Extend 到3月15，谢谢大家。
我也隔壁间而已。
乱动它的手，对对对，给它弄掉。而且我以前用的地方是这个地方，所以我也不敢乱动。以前你说以前我当地在的时候也用过那个什么中控室，中控室我有控过。在这边当地没有，我在其他地方，那一样有中控室，比这个还大间的，哪个地方？对啊，虽然都是一个什么，就是音量盘跟一些电线，但是就是还是怕乱动。因为里面那个蛮简单，就是几个电关掉，这样子就过去。这边的很棒，对，一定要先给他拜个码，不能乱动。明天那边也加一个电脑，然后邀请一个那个贵宾账号给他们，那边都不知道谁。因为他都没有，他还要再借一台啊，就看有谁要用，他也要听就拿他一台用，比如说志伟，然后那边状况到底怎么讲？志伟说那边因为他麦克风没有拿起来，他那边被拒了。
Okay, all right. Yeah.
一个是说借一个别的让他听，
And I think that in the
我的想法是说，反正这边就照着原样，然后那边就弄一个为什么邀请就好，他看谁要出，假如自我要就要自电脑去加里面去弄。看他决定，因为如果用 Webex 的话，那这个就声音就不到，然后。本来声音就不能传，只是那边再多加一套电脑，跟你放这样子。反正我明天也没会嘛，就把我们这一台拿过来。今天也没有。
Most operation is University of Kyoto volcano program. I think most operation is on site. Yes. There is really nothing.
那个啦，那个啦，是要先给一些专家。我已经给你了，
One
给你。我刚才说弄，
是
我意思说
from Nagoya University.
啊，弄下来他会。
I know him very well.
今天
He's a new faculty member at Kyoto. Yes. He's on campus.
So I guess I can stop at both ways.
Yeah.
No, but we will look at the Sakurajima for sure.
Oh, Sakura.
不是啊，我刚刚是说一直洗那个。那没有，那倒没有啊。
I've been there
不
once.
是打到下礼拜啊。
But the deployment that you mentioned is
你在跟他说我想要，还是说我们在不在？
by the local group.
我刚刚看好像。
Oh, Sakurajima, they have Kyoto University staff.
他其实就已经把他觉得不适合杀掉，然后有一些他只是说他觉得好像还可以保，所以那几项。
It's a very impressive operation.
他旁边会有人说，
Well,
那我就来保
I
留
don't
下一次
know
看。
exactly what, but my impression is Sakurajima operation is
改
more,
过了，改过了，有改很多了，可以
you
改
know,
可以给他
they are really monitoring
给
it.
X 因为现在
Okay, it's dangerous. But in case of us, up until
所以
recently,
是说
it
现
is
在
not
这个版本
dangerous.
可以先
So
divide 跟 H
it's
跟
more, you
对
know,
啊，因为你
standard
总不能等到
organic
最后才跟他
study.
讲，那可能已经剪
But
辑。
Sakurajima
最后其实
那如果下一代有改，
all
应该
telemetry.
不会改太多啦，就
下一代不要给他们看。
没有不行啊，他们还是
看了
不要再看小改一下，他们刚刚不会放步骤，而且说其实说真的，其实就是
好，那我就改哦。
时间到就要砍了，像这个像现在这个时间就要砍，现在砍就要定时，后面改。
Because I saw that you like to some and it's not too far.
I cannot travel too much. I get tired.
So I can't
All right. Well, nice to see you. Good. Have a good trip.
Okay. Hiroo Kanamori, thank you very much. Yeah, hope to see you tomorrow.
Okay.
Yeah.
I will continue.
Okay. See you.
All right. See you then.
Oh, by the way, this is Ray Jin. So for the undergraduate class in engineer, you'll be the one in charge.
Okay, you are here today. So
Right.
it's not going to be very difficult.
But don't worry, you didn't catch everything at once. So a couple times is necessary.
It's slightly different. Well, I started out with very different material. But then after having written it, well, the important thing is important. So,
Yeah, but indeed our undergraduate students will be like sophomore, senior. Some of them even only have like one semester for 6 months.
Okay.
Very, very beginning. And I don't know how much they remember. Yeah. So if anything difficult, yeah, yeah, you go on there.
okay.
你今晚上是什么情况？
哎。
好吧，那就先这样了，就先去。
So you get your